We often think of history as something written in books, carved into stone by human hands. But the Earth itself holds a much older, more dramatic story. Deep below the choppy surface of the North Sea, familiar for its oil rigs and fishing fleets, scientists have unveiled an astonishing secret. It is a scar left behind from a cataclysmic event millions of years ago. This discovery is like finding a lost chapter in our planet's autobiography, filled with cosmic violence and profound change, hidden for an immense stretch of time. Imagine a vast circular structure buried under nearly a kilometer of mud and rock at the bottom of the sea. For decades, its true nature remained a mystery. Geologists saw strange patterns in their data. They were not expecting evidence of an object from outer space. This hidden feature, now named the Silverpit crater, is the first impact crater identified in UK territory. A reminder our island story connects to the cosmos. This incredible find began not with a bang, but with a quiet moment of curiosity in a laboratory. A scientist looking at seismic data, the echoes sent deep into the Earth's crust, noticed something peculiar. The data painted a picture hard to explain with normal geology. It showed a depression with a distinct central peak, the hallmark of a high-velocity impact. It was a thrilling moment of realization. The team knew they were looking at something special, a feature that could rewrite regional geological history. It was the beginning of a scientific detective story, one that would take us back 65 million years. The unveiling of the Silverpit crater is a testament to modern science and our desire to explore and understand our world. Even in a well-mapped, economically important region like the North Sea, monumental discoveries still await. This is not just a story about a hole in the ground, it's about a violent event that connected Earth to the wider universe. It challenges us to look at familiar landscapes and seascapes and wonder what other profound secrets they might be keeping, buried deep and waiting for the right tools and the right questions to bring them to light. So what exactly is a crater? A crater is a bowl-shaped depression on a planet or moon, after a smaller object from space, like an asteroid or a comet, crashes into it. Think of it like the mark left when you drop a heavy stone into thick mud. The impact blasts away rock and soil to form a circular hole. On the moon, with no atmosphere, craters stay perfectly preserved. They record the constant bombardment of the solar system. On Earth, finding craters is much harder. Our planet is constantly active. We have wind, rain, ice, plate tectonics slowly move continents and can bury or destroy ancient features. That makes Silverpit, buried under sea and sediment, remarkable. Sea and mud acted like a protective blanket, preserving the shape. Scientists see several telltale features confirming an impact. First, the overall shape. Data show a series of concentric rings, ripples frozen in stone. That's a classic large impact sign. Second, a distinct central peak in the depression. The peak forms when the ground behaves like a liquid under immense impact pressure. Rebounds upwards seconds after collision, then cools back to solid rock. This structure differs from other geological processes. Volcanic calderas exist, but they don't have this ring plus peak combination. Salt domes can make circular patterns, but they lack these impact characteristics. Geologists compared Silverpit to known craters and to computer models of impacts, ruling out other causes. All evidence points to one conclusion: something from space hit this exact spot a very long time ago. The Silverpit crater is located about 130 kilometers or 80 miles off the coast of Yorkshire, hidden beneath the waves of the North Sea. It lies under a region known as the Southern North Sea Basin, an area that has been extensively surveyed by the energy industry. The crater itself is buried deep, lying beneath about 800 meters of younger rock and sediment, deposited over the 65 million years since it formed. This protective covering is the reason it remained hidden for so long, but it is also the reason it is so well preserved. It is a geological time capsule, sealed away from the world. When we talk about the size of this feature, the numbers are truly mind-boggling. The main inner depression of the crater is about 3 kilometers, nearly 2 miles across, but the seismic data reveals a much larger system of faint concentric rings that extend outwards from the center. This entire disturbed area stretches for more than 20 kilometers, about 12 miles from one side to the other. To put that into perspective, if the crater were on land, it would be large enough to comfortably contain a town the size of Windsor or Colchester. It is a monumental feature, a testament to the incredible energy that was unleashed on that fateful day. The location of the crater is also significant. 65 million years ago, during the late Cretaceous period, the world was a very different place. Sea levels were much higher than they are today, and much of what is now Europe, including the area of the North Sea, was covered by a warm, shallow sea. The asteroid, therefore, did not strike dry land. It plunged into water that may have been anywhere from 50 meters to 300 meters deep. This detail is crucial because the presence of water would have dramatically changed the nature of the impact and its immediate aftermath, creating a unique and complex sequence of events. Visualizing this location helps us appreciate the scale of the discovery. Imagine sailing out from the Humber estuary, far beyond the sight of land, into the heart of the North Sea. Below your vessel, beneath hundreds of meters of water and then almost a kilometer of solid rock, lies this immense scar. It is a silent monument to a moment of cosmic violence that occurred when dinosaurs still roamed the Earth. Its position, submerged and then buried, protected it from the glaciers that would later scour this landscape during the ice ages, preserving its delicate features for modern scientists to find and interpret. Let us travel back in time, 65 million years, to the moment of impact. The Earth was a warmer, greener world, dominated by dinosaurs. In the skies, pterosaurs soared. In the shallow sea covering what is now northern Europe, giant marine reptiles hunted. Suddenly, a new light appears in the sky. It grows brighter and brighter, a terrifying star appearing in the daytime. This was an asteroid, a rock likely several hundred meters in diameter, hurtling through the atmosphere at a speed of thousands of kilometers per hour. It would have glowed white-hot from the friction of its passage, a messenger of destruction from the depths of space. The asteroid slammed into the shallow sea. The initial impact would have been almost instantaneous and unimaginably violent. In a fraction of a second, the asteroid and the water it hit were vaporized, along with a huge amount of the seabed rock. This created a colossal explosion, many times more powerful than the largest nuclear bomb ever detonated. The blast would have sent a blinding flash of light and an intense wave of heat across the region. Any creature on the nearby coastlines, had there been any, would have been incinerated instantly by the thermal radiation released by this cataclysmic event. The impact didn't just create a hole, it created a shockwave of immense power. This shockwave would have traveled outwards through the water, through the air, through the solid Earth itself. The impact into the sea would have generated a mega tsunami. A gigantic wall of water, perhaps hundreds of meters high, would have radiated outwards from the impact site, traveling at the speed of a jet airliner. This colossal wave would have crashed onto the coastlines of what are now Britain and mainland Europe, scouring the land clean for miles inland and causing unimaginable destruction to any coastal ecosystems. Simultaneously, the explosion would have thrown a vast plume of material high into the atmosphere. Billions of tons of vaporized rock, superheated water, pulverized sediment were ejected miles up into the sky. This dark cloud would have spread out, blocking the light from the sun. As the heavier debris began to fall back to Earth, it would have rained down as superheated rock and glass, potentially starting widespread fires across the continent. The day the sky fell was not just a single moment of impact, but the beginning of a period of dramatic and devastating environmental change. The discovery of the Silverpit crater is a wonderful example of how scientific knowledge can come from unexpected places. The story begins not with astronomers looking for craters, but with geologists working for the energy industry. For many years, oil companies and gas companies have explored the North Sea, searching for resources trapped in the rock layers deep beneath the seabed. To do this, they use a technique called seismic reflection surveying. It's a bit like creating a medical ultrasound for the planet, allowing us to see what lies hidden deep underground. The process involves a special ship that travels across the sea, towing a device that releases powerful sound waves, or seismic pings. These sound waves travel down through the water and into the layers of rock below. Each time the sound wave hits a different type of rock layer, some of its energy is reflected back up to the surface. The ship also tows long cables fitted with sensitive microphones called hydrophones, which listen for these returning echoes. By measuring the time it takes for the echoes to return, scientists can build up a detailed, three-dimensional map of the geological structures. It was while examining one of these three-dimensional seismic datasets that two scientists, Philip Allen and Simon Stewart, noticed the unusual feature. They were looking at data from a part of the North Sea called Quadrant 34, a routine task in their work. But the image on their screen was anything but routine. It showed a clear circular depression with that telltale central peak. They knew that such a feature was very difficult to explain through normal geological processes like faulting or salt tectonics. The resemblance to a complex impact crater was too strong to ignore. Their initial hypothesis was met with some skepticism, as is proper in science. They had to painstakingly rule out every other possible explanation for the structure. Could it be a collapsed salt dome? No, the surrounding geology didn't support that. Could it be a strange volcanic feature? Unlikely, as there was no other evidence of volcanic activity in that specific layer of rock. After months of careful analysis and comparison with known impact structures, they published their findings in 2002. They had built a compelling case that this strange, ringed feature was indeed the buried remains of a giant asteroid impact. The discovery of the crater's shape was just the beginning. The next crucial step for scientists was to determine its age. This is where the seismic data proved invaluable once again. The three-dimensional maps created by the surveys don't just show shapes. They show layers of rock stacked on top of one another, like a giant layer cake. Geologists are very good at dating these layers. By studying microscopic fossils, called microfossils, recovered from boreholes drilled in the area, they can create a detailed timeline of the Earth's history. Each layer corresponds to a specific period of geological time. The Silverpit crater was found within a layer of rock known as the Upper Cretaceous chalk. This chalk layer was laid down at the bottom of the sea over millions of years. Crucially, the crater does not cut through the layers of rock above the chalk. This tells us that the impact must have happened after the chalk was deposited, but before the overlying tertiary-era sediments were laid down. By carefully dating these layers, scientists were able to narrow down the age of the impact to a window of time between 60 and 65 million years ago. This dating is incredibly important for understanding the crater's context. This timing places the Silverpit impact right around the same time as one of the most famous events in Earth's history, the Cretaceous-Paleogene or KPG extinction event. This was the mass extinction that wiped out about 75% of all species on Earth, including the non-avian dinosaurs. This event is strongly linked to the impact of a much larger asteroid, which created the massive Chicxulub crater, now buried under Mexico's Yucatan Peninsula. The fact that the Silverpit crater dates to the same period raised an electrifying possibility. Could it be related? This led to a fascinating scientific debate. One theory proposed that the Silverpit impact was part of an impact swarm. Perhaps the object that hit the Earth 65 million years ago was not a single asteroid, but one that had broken up into multiple pieces before it reached our planet, resulting in several impacts around the globe at roughly the same time. While more research is needed to confirm this, the discovery of Silverpit adds a crucial piece of evidence to the puzzle of this tumultuous period in Earth's history. It shows that the end of the Cretaceous may have been even more violent and complex than we previously imagined. The discovery of the Silverpit crater does more than just tell us about a single event. It opens a window into the deep history of our planet and the powerful forces that have shaped it. It reminds us that Earth's story is not just one of slow, gradual change. It is also punctuated by sudden, violent events that can alter the course of life in an instant. For a long time, the idea that catastrophes from space could play a major role in geology and evolution was considered radical. Discoveries like Silverpit have helped make this idea a central part of our understanding of Earth's past. Studying craters like this helps us learn about the processes of impact cratering itself. Because Silverpit is so well preserved, it provides a perfect natural laboratory. Scientists can use the detailed three-dimensional seismic data to test their computer models of how craters form. They can study the central peak, the terraced walls, the outer rings to better understand how solid rock can behave like a fluid under extreme pressure and heat. This knowledge is not just useful for understanding Earth, it helps us interpret the craters we see on other planets and moons across the solar system, Mars, Mercury. Furthermore, each new crater we find adds another data point to our global map of impacts. By finding more craters and dating them accurately, we can start to build a better picture of how often the Earth is hit by objects of different sizes. This helps us understand the level of risk our planet faces over long timescales. It moves the idea of an asteroid impact from the realm of science fiction into the realm of natural hazards, alongside earthquakes, volcanoes. The Silverpit crater is also a powerful lesson in scientific discovery. It shows that even in one of the most intensely studied regions on the planet, huge and significant features can lie hidden right under our noses. It highlights the value of looking at old data with fresh eyes and of being open to unexpected explanations. It's a story that encourages us to keep exploring, to keep asking questions, and to remember that the Earth always has more secrets to reveal. You might wonder why a 65-million-year-old hole at the bottom of the sea matters to us now, living in the 21st century. The answer is that understanding our planet's past is essential for safeguarding its future. The Silverpit crater is a stark and tangible reminder that the Earth exists in a cosmic environment that is not always benign. Asteroid impacts are a natural part of the solar system's machinery. While large impacts are rare, they are not impossible. They have happened many times in Earth's history, and they will happen again. Studying ancient impacts helps us understand the potential consequences of a future event. By analyzing the geology of the Silverpit crater and modeling its formation, scientists can better predict what would happen if a similar-sized object were to hit a shallow sea today. They can calculate the size of the tsunami, the extent of the atmospheric blast, the potential impact on the global climate. This information is not just academic, it is vital for assessing the risk that near-Earth objects pose to our civilization, and for developing strategies to mitigate that risk. The discovery also underscores the importance of planetary defense. Today, astronomers around the world operate telescopes dedicated to scanning the skies, searching for asteroids and comets whose orbits might bring them close to Earth. This is our early warning system. By identifying potentially hazardous objects years or even decades in advance, we give ourselves time to act. The story of Silverpit and the dinosaurs who had no space program is a powerful argument for why these sky surveys are so crucial. We are the first species on Earth that has the ability to understand this threat and do something about it. Ultimately, the Silverpit crater enriches our understanding of our own planet. It connects our local geology here in Britain to the grand sweeping story of the cosmos. It reminds us that the ground beneath our feet is not static, but has been shaped by incredible forces over immense spans of time. It is a story of destruction, but also one of resilience. Life on Earth survived the Silverpit impact. It survived the even bigger Chicxulub impact. The planet recovered, and life adapted and evolved. This ancient scar, hidden beneath the North Sea, is a profound lesson in the Earth's capacity for change and renewal.